Hey there, folks. Let's do these homework problems for 4.4. We'll do the first half of them. And I'm sorry, my voice is a little low, but I'm kind of fighting off laryngitis, so bear with me. Okay, here in problem 3, we've got 15 students make a field trip for snacks. The chaperone has brought 6 nut crunch bars, 6 chocolate bars, and 3 toffee bars. Question A says, how many ways may the bars be distributed so that each student gets exactly 1 bar? So what we're talking about then, we've got our 15 students. This is an arrangement of the three different types when we have a fixed number of each type. And so the way to handle this is the multinomial coefficient. We've got 15 things, and we want 6 of one, 6 of one, and 3 of the other. So this is 15 factorial over 6 factorial, 6 factorial, and 3 factorial. And so 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7, and the rest will take care of one of the 6 factorials. And then we've got the other 6 factorial and the 3 factorial. So let's see, 6 goes into 6 once, into 12 twice, 5 goes into 15 3 times, 4 goes into 8 twice, 3 goes into 9, well, just take care of that 3 right there, take care of that 2 right there, 3 goes into 9 3 times, take care of that 2 right there. And so I think when you do all this out, you get 420,420 different ways to distribute those bars so that each student gets 1. Now, the other question is different. It says, how many ways may the bars be distributed to the 15 students with no restriction on how many each student receives? So here what we're looking at are 3 tasks. Right, we're going to distribute the nut crunch bars. Okay, and then what's distinguishable here, the different types are the students. We've got 15 different students, and so we think about the crunch bars, the 6 crunch bars being the 6 stars, and then the different students being the type or the different so that's the bars, right? So we'll need 14 bars to do this. So we distribute the crunch bars, the 6 crunch bars, then the 6 chocolate bars, and then the 3, oops, get ahead of myself, 3 toffee bars. Okay, so for the nut crunch here, alright, we've got a multi-set of length 6, that's the 6 crunch bars, that we want to put into 15 different types, and the types would be the students. That's our 15 minus 1 bars. So this is 6 plus 15 minus 1, stars and bars. Choose 6, or simply 20 choose 6, which I believe is 38,760. And that would be the same answer then for the chocolate bars, because it's the same number. And then for the toffee bars, we've got the 15 students, and we want a list of length 3. So this is 3 bars and 15 minus 1 bars, 3 stars, 15 minus 1 bars. So this is 17, choose 3, which I believe is 680. So then the total would be this 38,760 squared times 680. It's squared because you've got the 6 Nut Crunch bars, and the 6 chocolate bars, and then the 3 toffee. And so this is a fairly big number. See, a million, billion, trillion, 1,000,000,000,000, 21,589,568,000 different ways of doing that. Okay? Problem 4 says, okay, we've got a 4-digit house number that contains no zeros. The number has 3 distinct digits. How many such numbers are there? So, with 3 distinct digits and a 4-digit number, we're going to have to repeat one of those numbers. So I think the way we approach this is, first we pick the 3 non-zero numbers, okay, distinct ones, and then we pick the one that's going to be repeated, and then we place them, okay. So we've got 9 digits, not counting the 0, right, to choose from, and the order doesn't matter. So we're going to choose 3 of those. And then I have to take, of those 3, I need to pick one, or choose one, that will be repeated. And then I'll use the multinomial to place them. So this is 9 factorial over 3 factorial 6 factorial times 3 factorial 1 factorial 2 factorial, and then 4 factorial 1 factorial 1 factorial and 2 factorial. So that goes, that's good. This is just, let's see, 6 factorial would leave me up here with 9 times 8 times 7. And then the 2 factorial is just 2. So that would leave me with 4 times 3. And then this would go into 4 once. So I think what you end up with, if I do all my calculations correctly, 3,024 different ways of doing that. Okay. Problem 5 is similar. Let's say a house painter removes the brass numerals from the home at 72,712 Main Street. Later, the painter forgot the numbers and tried to recall them by rearranging them. How many different house numbers can be formed by rearranging 72712? Well, this is again a multinomial coefficient where we have 3 separate things, but we have some repeats. So this would be of length 5, and we'd have 2 7s, 2 2s, and only 1 1. So 5 factorial over 2 factorial, 2 factorial, 1 factorial. 5 times 4 times 3, then times 2 takes care of one of those factorials, and that'll take care of the others. So this is 30 different ways they can be arranged. All right. Problem 6 talks about the game of Mastermind, and where one player selects a code by inserting any combination of 4 pegs in a row of 4 hidden holes. There's 6 colors of pegs to choose from. The second player tries to guess the code by repeatedly inserting 4 pegs in a row and receiving feedback from the code maker on the number of pegs of the correct color and the number of pegs in the correct position. Suppose CodeMaker first selects 4 pegs from the code from the large supply of pegs of 6 colors, then determines the order pegs determines the order the pegs will be placed in the 4 holes. So question A kind of goes like that. How many ways may the code maker select the 4 pegs for the code. There are 6 colors to choose from. We're going to choose, and we can choose repeats. So this is 6 types, multi-choose 4. So 4 stars and 6 minus 1 bars. 9 choose 4, and if I'm not going to go through all the work here, but I believe this works out to be 126. Okay, and I actually just did that by punching in my calculator. Problem B asks a different question. It says how many different mastermind codes are possible. Well, now this is more direct. This is the kind of thing we've done previously. I've got 4 slots. I've got 6 choices for every slot, right? 6 colors. So this is 6 to the 4th power. 6 times 6 times 6 times 6. using the fundamental counting principle. So this is 1,296. Okay. Problem 7 says, okay, we've got 5 children and they each order a small drink from a stand that offers 7 types. How many outcomes are possible? Well, again, we got first child, second child, third child, fourth child, fifth child, and every time they go up to the stand they've got 7 types, right? So this would be 7 to the 5th power, which is, I believe, 16,807. Part B is actually kind of a silly setup because somebody taking care of 5 kids would never do this, but they decided to just get a selection of 5 small drinks from the 7 available and possibly get even repeats. How many ways may the chaperone place the order? Well, because we can repeat these things, right? And there are 7 to choose from, and we can multi-choose 5. Then this is 5 stars plus 7 minus 1 bars, or 11 choose 5, which according to my calculations is 462. Okay. And I think I'm going to stop there. We've got some other problems, but I want to kind of break these up into parts. So I will stop right there for the time being, and we will come back to problem 8 in the next lecture.